In this section we deal a lot with circles, which will come up quite a bit as we end the year, especially in Chapter 12. So let's start off with a bunch of quick vocabulary you should already know. First, you all know that this is a circle. Earth-shattering, right? Every circle has a center, which is, guess what? Right in the center of the circle. You'll often have the center of the circle shown, and it will be labeled like it is here. If the center has been labeled, then you can name it. In this case, you could say Circle A. That certainly works. However, it is often pretty common for the center to be labeled with an O instead, presumably since it resembles a circle. It definitely isn't necessary. Circle A was perfectly fine, but you will see Circle O a lot. Now to get to the symbol part. You don't want to be writing the word circle all the time, so we have a symbol. It is often the case that the symbols resemble the shape they are replacing. That is true of triangles, parallelograms, parallel lines, and many more. But we can't do a simple circle as a symbol. That would be confusing, especially if a circle is labeled with an O. So that isn't right. They do want a circular shape, but they don't want the confusion. So they settled on this, a circle with a center drawn in. That's the actual circle symbol. You need that point in the middle. Now back to vocabulary you should know. All of these line segments are the diameters of the circle. They all go through the center, and all of the endpoints are on the edge of the circle. But you already knew that already, right? Then we have a radius. All of these are radii, or radiuses if you prefer. Both are correct. You probably already knew that, too. Make sure you know that a radius is half the length of a diameter, or that a diameter is twice as long as a radius. What about congruent circles? Here I have Circle A and Circle B that look pretty congruent, but how do we know for sure? It is much easier than having to do SSS or SAS or whatever for triangles. Congruent is still same size and same shape. All circles are the same shape, so all we need to do is check if they are the same size. To do that, you generally check the length of the radiuses. Here I have drawn in a radius for each circle. You just need to check to make sure their lengths are the same. That's it. If the radiuses are the same length, that is all you need in order to say Circle A is congruent to Circle B. Very easy. Since diameters are always twice as long as radiuses, you can also check if diameters of the circles are the same. That is also somewhat common, but not quite as common as radiuses. Next up are concentric circles. Con meaning with, and centric meaning center. So concentric circles are circles that have the same center like these shown here. One of the more common things you have seen with concentric circles is a target like this one here. This one happens to be an archery target, but that's all there is for concentric circles. They are just circles that share a common center. A central angle is exactly what it sounds like. It is an angle whose vertex is in the center of the circle. This red angle is an example of a central angle for this circle. That's all there is to it. Now we finally come to arcs. Arcs dominate the rest of this lesson. An arc is an unbroken piece of a circle. All of the colored segments being drawn on the circle are arcs. We are going to be doing two calculations with arcs in this lesson, but the first one is the easy one. Arc measure. If an arc is an unbroken piece of the circle, the arc measure tells us how much of the circle we are talking about. I can see from this picture that we have a red arc, but I want to know how much of the circle is covered by that red arc. That's what arc measure does. By definition, the measure of an arc is equal to the measure of its corresponding central angle. So I should probably draw in that central angle. The measure of this central angle happens to be 64 degrees. Since the measure of the arc is the same as the measure of the central angle, I know that the red arc must also be 64 degrees. What is that telling us? I know that it is 360 degrees to go around the full circle. Since this red arc measures 64 degrees, that is saying that this arc is 64 out of 360, or 8/45ths, the size of the whole circle. This arc is an unbroken piece of the circle. The 64 degrees just tells us exactly how much of that 360 degrees we have. Now let's work on classifying arc. When you see the term minor arc, that should be bringing to mind something small. And this blue arc here is a minor arc. But we need a more specific definition. The measure of a minor arc is greater than 0 degrees, but less than 180 degrees. If a minor arc sounds small, then a major arc should sound like it is big. And it is. This orange arc here is a major arc. Specifically, the measure of a major arc is greater than 180 degrees but less than 360 degrees. In between those two, we have a semicircle. A semicircle is exactly half a circle. As such, the measure of a semicircle is exactly 180 degrees. In order to name an arc successfully, I need to have at least the endpoints named. So I have done that here. So let's say I want to name that arc. You might think it should be arc AB. There is actually an arc symbol, so you could write that also as this. It looks like a little arc. Isn't that cute? But we have a problem. Have you figured out what it is? What's the issue with arc AB here? The problem is arc AB could be referring to two possible arcs. There is a red minor arc on this side, or a blue major arc on this side. When I say arc AB, which one do I mean? What do you think? Do you think it's the red arc? Do you think it's the blue arc? Do you think you need to do something else so that we can differentiate which one we are talking about? Any guesses? If an arc is only named with two letters, then it is referring to the minor one. So in this case, we can get rid of the blue one. Arc AB is referring to the red minor arc. One last thing about this minor arc. Just like angles, you can name them in either direction. This arc could be named either arc AB or arc BA. Either is fine. But what if I had intended to do the blue major arc instead? In order to successfully name this arc, I actually need to add another point somewhere in the middle of the arc. With point C added to the picture, then I can name my major arc. Either arc ACB or arc BCA would work successfully. Make sure you go in order. If you trace in the order of the points you named, it should successfully trace your arc. Remember, minor arcs are named with 2 letters. Major arcs must be named with 3 letters. But what about semicircles? If I wanted to name the semicircle, could I use arc XY here? Hopefully you figured this out, but that is no good here. I don't know if arc XY is referring to the semicircle on the left, this yellow one here, or whether it means the semicircle on the right, the green one here. Semicircles must be named with 3 letters too, so I better add in a couple of letters now. With W and Z now in the picture, literally, if I wanted to talk about the yellow semicircle on the left, I would say arc XWY or arc YWX. If I wanted to talk about the green semicircle on the right, I would say arc XZY or arc YZX. For adjacent arcs, it works very similarly to adjacent angles from nearly the beginning of this course. Adjacent angles were, generally speaking, 2 angles right next to each other, but no overlap was allowed. The same thing is true of arcs. Officially, adjacent arcs are arcs of the same circle which have exactly 1 point in common. That basically says right next to each other with no overlap. In this picture, arc AB is adjacent to arc BC. This is only really used in the next postulate. Like most postulates, this one is completely common sense and gives you that, well, duh feeling. The arc addition postulate says that the measure of the arc formed by 2 adjacent arcs is the sum of the measures of the 2 arcs. In this specific case and picture here, that means the measure of arc AB plus the measure of arc BC is equal to the measure of arc AC. You should already know this many times over, but just make sure that you remember circumference of a circle is 2 pi r, or some of you may prefer to remember it as pi times the diameter. Either way, this is a formula you need to remember. We will use it here in a second. We are finally to the last bullet point, arc length. I told you earlier we would be measuring arcs in 2 different ways. Arc length is the second way. Let's look at what the difference is in the 2 ways to measure an arc. For a full circle, we know that the measure is 360 degrees. It is 360 degrees to go all the way around it. For an arc, the measure is telling you how much of that 360 degrees you have. Those are measures. They are measured in degrees. That's the first way to measure a circle or an arc. For a whole circle, circumference is a completely different measurement. Circumference is not measured in degrees. It is how long the line would be if you could unroll the circle and lay the line segment flat. Let's say I had a cute little ant, and that's about as cute an ant as you'll find. If that ant wants to take a stroll around the circle, circumference is telling us how far that little guy had to walk to make it all the way around the circle. Circumference is a linear measurement. It will be measured in inches, meters, or the like. It's a completely different measurement for a circle compared to its measure. Similarly, arc length is a linear measurement trying to figure out how long an arc would be if you laid it flat. Or in the ant example, how far a little guy here has to walk in order to cover the whole arc. That's what arc length is. The trick is how to calculate it. You can actually puzzle it out for yourself if you really think about it. Here are the pieces you need to consider in order to puzzle it out. The circumference measures how far it is to go around the circle. The measure of an arc tells you how much of the circle you have. Those are the 2 key pieces of information we need in order to compute arc length. Here is the formula. Note that there are 2 versions of the formula depending on which circumference formula you prefer to use. Also notice the pieces of the formula. This part is the circumference. It computes the distance around the whole circle. But we don't want the whole circle. We only want the part of the circle covered by our arc. The measure of our arc tells us how many degrees out of 360 degrees we have in our arc. That's the formula. Let's see it in action. Here I have put the measure of the arc and the size of the circle, the 2 pieces of information we need to calculate arc length. So let's plug those pieces of information into the formula. 30 pi is the full circumference. It is how far it is around the whole shape. We have 132 degrees out of 360 degrees, and the degrees will handily cancel away, leaving us with this, 11 pi millimeters. That's the arc length. Don't forget your units.